Hello, in this video we'll be looking at waves, and in particularly the graphical let's just call it graphical representation of a wave. Now let's start with a particle. Now waves consist of particles. So here we have a wave. And often is the case, especially for transverse waves, in which the motion of the particles are up and down. We have a wave like this going in that direction, and for transverse wave, even longitudinal waves can be represented by these graphs, but it's easier to think about as a transverse wave for now. We have particles moving up and down, or particles that are oscillating. Okay, and although the wave goes that way, each particle will oscillate up and down. So what we're going to do is we're going to think about it graphically as if would represent just one particle oscillating up and down. What will the graph of that look like? So now first of all, a particle oscillating up and down, they're often thought about as moving in something called simple harmonic motion. Okay, now this is not part of your course, don't worry about it, but I'll explain it briefly. Simple harmonic motion is a motion in which at every point in its path, this wave, there will be a force acting towards its equilibrium point. So here is say this is the equilibrium, the middle of the path of the particle, and if at one point the particle is there, and this is its complete path up and down, there will be a force always acting towards the center of its motion, or the equilibrium. So there'll be a force acting in that direction. Also, the force always acting to restore it to where it started. The force will also be proportional, which is this symbol here is proportional to the displacement x from the equilibrium. Okay, which can give you a formula F equals minus kx. Now this is a little bit of aside on simple harmonic motion, but we'll come back now to looking at the particle. So, how do we represent it? So what we will do, we will represent the motion of the particle oscillating up and down against time. So if we have this here as the displacement, and this is the time. Now time is usually in seconds, displacement, but not always. Sometimes, check the question, they could give you the time in milliseconds. Okay, or they might write times 10 to the minus 3. So be careful with that. Displacement often given in meters or millimeters, etc., etc. Again, be careful when they do not use SI units of meters or seconds. So if we represent the motion of the oscillating particle, so this is the center and it's oscillating between a maximum and a minimum, we'll find that the path becomes sinusoidal. That is, it follows the equation of a sine graph. Okay, so this is against time displacement. So at any time the particle is moving, you'll see that its displacement will vary like this as time increases. Watch time does. Okay, now this will be here. You'll see that between that distance between the equilibrium, the center of its motion, and the top is known as the amplitude, which is the maximum displacement, and of course that is the amplitude in the negative direction. Also, the distance between two peaks, well, not the distance because it's time, the time rather, be careful, between two peaks, if it's a time graph, is known as the time period, period t. That is the time for it to repeat itself in the cycle. So if a particle, doesn't matter where it is, it could be between there and there, that is also the time for a complete oscillation. So in fact, if there's a particle is there in its oscillating path, it will go to that end, back through in that direction. When it goes back to there again, that is the time for a complete oscillation. And of course, from there we have the frequency. Frequency is the number of oscillations per second is given as 1 divided by the time period. Okay, now that is how to represent the motion against time. Another way that we can represent motion is for the whole wave, all the particles, as if they are well, they're sort of joined together. They have an influence on each other. They have some forces between them. So if you think about a water wave, the particles, even though they're going up and down, they do have a connection between each other, which makes the particle next to them move up and down. So if we take a snapshot in time, so we stop time. So we stop time, however we manage to do that, or if you like, a snapshot, a photograph, we'll find that the graph looks very, very similar. But instead of being against time, we have distance along the wave. So you think about, if you look out at a water wave, you see a pattern that looks very much exactly the same pattern as if it was against time. Now this distance could be in meters, and the displacement, the up and down, also in meters. This time, the distance between two parts in the cycle, it could be peak to peak, so those are the peaks, or trough to trough, or any other part of the cycle. The distance between these two places, where like that, where it's the same part in the cycle, that is in fact given by the symbol lambda, which is the wavelength. Okay, that is the wavelength. And what we'll find is that we can link the idea of the time and the wavelength together by the formula that the velocity of the wave is simply equal to the frequency multiplied by the wavelength. That's linking the two together. Again, of course, remembering this here, still here, that distance there is still the amplitude A.